12 general 1.1 diffraction. Question 1. The diagram below shows a series of waves approaching an opening in a barrier. The waves reach point P as a result of diffraction. So as a result of diffraction. Which diagram best represents the shape and the direction of the waves after they encounter after they pass through a small opening in a barrier? So it is this one. So it is option 4. Number 3, the process by which a beam of light spread out as a result of passing through a narrow opening, also diffraction. What type of pattern is produced by single slit diffraction of coherent light? So also it is a wide central band. So here we have, it is this one, this shape. So it is a wide central band with narrower bands on either sides. Okay, question number 5, it is not included. Question 7, we have a monochromatic light with wavelength equal to this much wavelength, and this far from the screen, and the width of the the slit is 0.8 millimeter. We need to find what is the width of the central band. So basically it is by applying this equation to lambda L over W, replacing everything by its value, 2 times 546, it is in nanometers, so I'll multiply by -9, just a minute. Again, so it is 2x1, which is 2 lambda L over W. The wavelength is 546 times 10 to the power of -9 because of the nanometer. The distance is 68 centimeters, so I'll also convert from centimeters to meters. And also not to forget that the width is in millimeters, so I need to also convert. So these are the 3 conversions that I have to do. Finally, the answer is 9.2 times 10 to the power of -3 meters, which is D. Question 8. A light of 410 nanometer shines through a single slit, again with diffraction, falls on a flat screen as shown in the figure below. The width I have and the length from the slit to the screen. So what is the width of the central band, bright band? So also 2x1 is equal to 2 lambda L over W, which is 2 times 410 in nanometer. L this time no need to be converted, it's already in meters, and the width is also given in meters, 3.8 10 to the power of -6. It will give me 0.063 meters. Option D. Question 9, we don't need. Question 10, we don't need. Question 11, monochromatic light passing through a single slit will produce a diffraction pattern different from a double slit. So because on the double slit, the pattern, the central bright band is not double in length and width, so they will be different, and eventually we can see them in here. They're two quite different patterns. Question number, let me go here. Question number 12. What causes a diffraction grating to produce interference pattern? That's because tiny scratches that act like each one a single slit. Question 13. Diffraction grating have large number of closely spaced slits. To do what? To increase the intensity of the diffraction, to produce sharp images, to produce colored fringes? No. So actually A and B are correct. Question 14. I've got a diffraction grating of 6,000 lines, so that's the number of lines per centimeter. So what's the distance between the two lines? So I'll apply the equation d equals to 1 over n, which will give me 1.6 10 to the power of negative 4, which is option. Question 15. Which number of slits in diffraction grating produces the narrowest lines? Narrowest lines means I need sine of theta to be the smallest. This means I need the largest number per unit length. So the first one is 600 slits per centimeters, so times 10 to the power of 2. Because the centimeter is down, it goes up to become positive 2. The second one is 600 times 10 to the power of 3, which is per millimeter. The third one is 4,000 times 10 to the power of 2. And the last one is 4,000 times 1. So the largest number is this one. Later, question 19. A grating has slits that are this much apart. Okay, what is the angle for the first order? So the first order means m. For the light of wavelength, also given. So d sine of theta equals to m multiplied by lambda. 0.055 times 10 to the power of negative 3. That's because I have millimeter, multiplied by sine of theta equals to the first order times 650 nanometer. I will end up with an angle of 0.68. So we have light that is viewed through a grating spectroscope. I've got the angle, I've got the first order, I've got the wavelength, I need the slit separation. So I'll apply my equation. I will end up having d equals to 1336 nanometers. Question 18. I have 600 nanometer light, so that's the wavelength, is incident on a diffraction grating that is ruling a separation d. The second order, m equals to 2, occurs at a diffraction angle of, let us find the angle. So d sine of theta equals to m lambda. This time m is not 1, so 2 times 610 to the power negative 9. I don't have my theta. D equals to 1.7 10 to the power of negative 6. I will have an angle of 45. Going to question 19, we have a grating has slits that are, oh, we done it. Question number 20. A diffraction grating that has 4,500 lines per centimeters is illuminated by light that has a single wavelength. A second order, this means m equals to 2, and the angle is given. What is the wavelength? So we apply the equation of the diffraction by grating, d sine equals m lambda. But first, before finding lambda, I need to figure out what is d. So given n, I'll go find first d, 1 over n. And not to forget that I need to convert from this centimeter to meters. Okay, so once I have d, I'll just put it in its place. So d sine of 42 equals to the second order multiplied by lambda. So I'll end up having 740 nanometers. And that's it. Yeah, thank you.